Very good morning. I'm just making a video walkthrough for the questionnaire what is shared for me. Probably this will give a clear clarity on both the sides and make things more easy. So I'll try to probably answer all your questionnaire in this video. I'll also attach the PDF which I'm being using here. So, going to the topic, rate limiting, I'll probably take one practical experience which have been used for this. In my previous org, which is so-called Book My Show, I use this rate limiting service in one of my business problems. So I'll try to cover that use case. I'll take examples, taking Book My Show into consideration, so that it will be easy for me to take you to the point what I'm trying to convey. So the first, I'll probably start with what rate limiting is, how it's impacting our business, what kind of operational overheads we had, what security concerns we face, and how we tackle this. So I'll just go with that, and then probably I'll deep dive into the solutions. And more in concern, I'll only take time to explain in detail about the sliding time window which we have implemented here. So before implementing rate limiting, I'll just walk through about our flow, the workflow or the business flow which happens. So all the requests which comes in for booking will pass via load balancer. We have our AWS zone, which has basically three instances. These are all auto scales, which are all Kubernetes spots, basically. So whenever the request comes based on the traffic and the request, these pods gets scaled up, and whenever the traffic goes down, they get scaled down. So this all happens automatically. Now here, the main important instance which I want to try to probably cover is only about the rate limiting part. So, what is the importance and what is the usage of rate limiting? Why it is so important for us from the business point of view, from the operational point of view, from the security point of view? I want to cover these 3 points in this video. So, generally, I have a user who tries to book their tickets. So all his requests passes via the load balancer and goes to any one of the service, which is so called as a booking service. And the booking service, what it does is once the user has initiated the ticket service, or once he has initiated the transaction, we block the particular ticket for 10 minutes or 15 minutes of time. So if I select a particular seat, till the payment is done, we block the particular seat. And once the payment is done, we come permanently block the ticket and give the ticket information or share the ticket information to the customer. This is how it happens. So this blocking of 10 minutes of time is something a critical thing for us from the business point of view. So generally, these actors or threat actors or bots, what they does probably is these actors or bots are not a legitimate users, who really don't want to book a ticket and make payment. Uh, they just want to play with our services. So they just tend to initiate transactions via the load balancer. Now, the system, if there is no rate limit, this is all explanation I'm giving without rate limit. The system will try to block the seat for that particular 10 minutes of time. Ideally, these customers are not a valid customer. They don't want to really pay and make the transaction complete. They just block it for that time duration. So what happens is when these bots, bots really induce lot number of transactions at a particular time slots. So what we have observed is there are really tickets available, but yet on the system, when we see on Book My Show platform, we see these are not available for a real customer to purchase, because the 10 minutes time frame which is there to block the seat till the payment happens, that time frame these bots and actors are utilizing it and not allowing my regular customers or genuine customers to buy the tickets. So we really want to stop this behavior. We want to limit a certain number of transactions for a particular user or for a bot. So that's when we thought that rate limiting is very much useful. More than the business, the other problem which we faced was the operational overhead. When huge number of transaction hits, when the traffic increases, which we think it was a genuine traffic, we used to expand our infra. It auto scales. But generally, when we relook at back, these are not a real transactions. They are just coming to hack our system. So Even though we don't have a real payment happening there, but our infra cost is increasing. So this is one of the biggest operational overhead which we used to face. Hence, this was a concern. So both from business point of view, where the seats are really shown as blocked because of too many requests coming from the bots or from the non-regular customers or illegal customers. In spite the tickets have been available at the theater end, at the event place. And second is the operational cost increasing. Third problem we also have is the security concern, where we throw certain coupons for the customers to utilize and get advantage during the festival time, other times. So it what happened, these bots used to utilize these coupons and make hundreds of transactions without paying, and we used to end up saying, hey, the rewards are not being utilized properly, but yet we see the reward is used. So there's various security concerns also which we faced during our implementation in 2015. So we thought there should be a solution which we have to keep in place. So that's when we thought of rate limiting. So rate limiting primarily is an entity which we designed where we can restrict number of requests per a user for a particular time frame. So for a second, we say 10 requests per second or 5 requests per second is what we have designed. And more than that request, if it comes, we put them in a queue. And we try to identify whether these requests are really legitimate or are they valid or not. If they're valid, we'll again process the queue. If they are not valid, we try to drop the request from the queue itself. So this is how we have designed this rate limiting use case. We'll probably go deeper on how we have implemented, but this is how the problem we have identified, and we are trying to put up a solution for this problem. Let's get on to the next slide. Right, and talk about the functional and non-functional requirements for this rate limiting concept. So that we don't miss any of the concepts. So under the functional part, we'll try to ensure that we take care the number of requests which have been served within a particular time window. So I think it's mentioned as 10 requests per hour, which I feel it's too high, too low. So I'll consider 10 requests per second. So I'll make sure that, our algorithm or the workflow works saying, hey, if there are 10 requests sent in a particular second or in a particular minute by any of the client, then we will try to compute that. And if anything is sent more than that, then we'll try to block that. That is how we will consider this workflow. And if at all there is, whenever the threshold is crossed, like, we have limited, it's only 10 requests to be sent. And if you cross the threshold, then probably we'll send back error message saying, hey, too many connections sent, or we have crossed the message. So a proper error message is also delivered to the customer or to the client level. This is what we'll try to check. And we'll try to also see this works in both local as well as a distributed system in productions where we have multiple clusters being there spread across different zones. We'll try to see that this works across distributed systems, and local also it works pretty well. So these are the two functional requirements which I'll try to cover. On the non-functional part, we'll see, I'm sorry. On the non-functional part, I'll try to see, ensure that the system is highly available and it's safe from all the external attacks. And whenever we are designing this, we'll also take care of the performance into factor. Without any latency, without impacting our user experience, we'll try to take this entire workflow. So these are the two functional and non-functional requirements I'm considering when I'm building this approach. Going on next, primarily, I'll also give you how this rate limit works, a top level overview, how we have defined how it works basically. What we do is we will have an interface where the admin or the owner of the accounts can specify initially what is your rate limit configuration. So you can set the rules. We call them as the rate limit rules. We can set the rules. You can set them in various ways, per account level, domain level, user level. So the various ways, I'll probably show some of the samples down the lane. We can set these rules and store them in the DB. So that is the one part of the activity which can be done. Then whenever the request comes and matches the rules, the counter is being computed. It could be per client, per IP address, or per IP address, per domain address, whatever way it is. There'll be a counter which keeps on, incrementing. So whenever the request comes, the counter increases. So Once it reaches the threshold, whatever we have given as a maximum number of hits or request accepted, once we reach that, it starts rejecting. So the counter is being counted basically once the rule is matched. Then, as I said, as it exceeds the threshold, will not be allowed to reach the origin server and the error page. This is how the overview of the rate limiting works across anywhere. We'll see what optimizations we do here and what considerations have taken. Before I start with the system design part, three important things which I'm considering is, how do we configure this rate limiter? As I already explained in the previous slide, do we consider this at an IP level, at a user level, at an account level? No, there are various ways to consider. So, where do we configure this? So, this is the first point. I'll probably take a hit. Next, what is the overall size? Because size matters, the memory computation matters. So what is the size of your system, what you're designing, how it takes? So I'll deep dive into these things when I start getting into the algorithm. And the next thing is, where do you place this on a client level or a server level, or in the middleware? I prefer to be as a middleware. I don't place it as a completely client side or the server side. The best portion I think always is once you move from the load balancer, immediately I have a rate limiting service there. Probably if you want authentication layer to be before, you can have one level of authentication layer before, and then you can have a rate limiting service. So I consider this to be a middleware between client and the server. But these are the three important criteria I'm trying to consider. I'll try to elaborate more on these criteria in my overall explanation. So as I told you, this is the top overview of how the entire workflow works here. So I have a user. Once a request comes in, we generate a unique client identifier. If it is authenticated, then I think the user ID itself can be taken as a unique ID. If not, if it is not authenticated, generally we also do for anonymous request. So we can generate one unique key for them. Could be a timestamp versus IP or something like that. A combination, we can do a hash map and get that unique key. So we first generate a unique key, which is sent to the rate limiting service. Basically, this is one microservice or a central service which acts like a platform service, can be integrated with any of the other services. So I see rate limiting is being used across various use cases. It could be used in blocking the request right away, what we are discussing. It can also be used in mail services where you want to prevent spams. You can also put your rate limiting control over this. So there are various places in the applications where you can use this rate limiting. So we can use this as a centralized service, as a platform service, and we can just give the instructions of integrating with any product, in an easier way. So I'm considering this as a microservice. Now, as I told you, this entire rate limiting depend upon the rules which we are defining. This is the rule service which I'm talking, and we have a service user who can update these rules, and all these rules get stored in the database. The database can be a Mongo or MySQL, whichever tends. But for entire real application, I don't depend on this storage. This is basically kind of a backup. I completely depend upon the caching layer, basically. Which basically I use it as Redis. So there's a throttling service which pulls the rules from the DB and updates the cache continuously. Other way, primarily with the recent upgrade we did was that whenever we use this rule service and dump that information into the DB, we first dump in the cache Redis, and then we keep a background job which runs at the background and pulls this data from the cache to the database. So this is also another way which we can use it effectively. So finally, the rules, whatever rules we are updating based on IP or user or domain, whatever is our logic, all these rules gets updated in the cache, and via the throttling rules retriever, using this service, we keep on updating them and pushing them to the rules DB, ensuring that this is in sync with us. So whenever the request comes with a unique key, in form of a unique key, the rate limiter service hits the throttling, the cache DB what we have, where it checks with the rules. If there's a perfect match with the rules, the counter is increased. And if it is not above the threshold, then the request is allowed. And suppose if the particular rule match counter is already there at the threshold, and that means we have already exhausted and there is no space for again moving, allowing any more requests, then that particular rules gets rejected. Now these rejected rules, we try to do some more operations on top of this, where we uh, throw customer saying, hey, there is a 429 error message show to the customer, or 503 error. Basically, generally we show 429 message to the customer, and these requests which are rejected are dropped into a queue, and we reprocess them. So sometimes there would be a legitimate customers, for some reason their request would have went into a queue. So let's say there's a login activity being done and he clicks submit and it just says, too many requests. Instead of bringing in too many requests, we say process is undergoing. And what we do is those kind of valid requests, we use certain ML machine learning algorithms and understand whether it's a legitimate request or a fraud request. And if it is a legitimate one, after certain time found, we reprocess this again to the rate limit too, so that that gets allowed. If it is completely fraud, we drop the request from the queue. So this is how the overall workflow happens. So overall, the major component I see, there's a one which is the rate limiter service, the microservice, which is the main decision maker for the entire flow. The rule service, which actually has a backend with the DB where it stores all the rules. The throttling service, which basically syncs, it's a kind of a background job, which basically syncs the data between the cache DB and the normal DB, so that if it is all the updated rules are there in the cache, it becomes easy for the rate limiting service to increment or decrement the counter, validate with the rules, etc. So we will also see the importance of the cache here in the rate limiter service down the lane. But this is how the entire workflow happens, right? So going to the next slide. In this slide, let's talk about some of the rules which we store in the DB, right? As I told you, we can have rules based on IP. It can be based on account, or it can be based on user base. So we'll just take some samples to understand how they are. So I can have IP-based rules saying /account/API/signup has 20 recs per minute, which means if I get a request from a particular IP and that request is hitting this URL from a particular IP, account/API for sign up. So I allow 20 requests in a minute. That is what this means. Similarly, if I hit this endpoint from a particular IP and I just allow only 20 requests per minute. That is how the IP-based request works. Whereas in the account base, I globally classify for a particular domain. So for app.mybooking.service.com, I have 20K requests per minute. At any point of time, I can allow 20K requests in a minute. It could be from any of the APIs, from any of the IPs, so as a global configuration. This is similarly in.mybooking.service.com. This is 10K requests per minute. So this is a global level configuration. This is a endpoint level configuration. So that's what. And similarly for user base, I have a specific use case where I want more throttling for some of the user IDs. They have some extra privileges. So I can say user based in the key value format where it says user ID, count, and start time. So I say Ramesh has max of 4 requests per minute, and in the times start time, this is a timestamp which has been there. So we keep on updating the timestamp so that difference would be always not more than a minute. In a minute, Ramesh always have access to 4 requests. So this is a user base. So we have these different ways where we can configure our rules. I'm just giving you an overview of how the rules can be configured. And then, as I told you already, I choose here limiter as a middleware, which is between client sends the request, then it goes to the ELB or the load balancer, and from there, the rate limiter takes it, validates it, which is the compute at the back, and says, hey, this is allowed request or not allowed. So the primary job of rate limiter is to just say yellow or not allowed. So what algorithm we use, what logic we use behind this, probably we'll discuss, but this is what it does. So it allows to the API servers, the processing happens and the request comes back. If it is not allowed, we just send back with a 429. That's how this works as a middleware. Going next, the interesting in this entire rate limiting concept is basically the counter. If you have observed, I'm being saying whenever a request comes, it matches your rule in the database or in the Redis DB cache. And if the rule matches, it checks with the counter. It checks with the threshold first. If it is under limit, the counter increases one by one, one by one. And ultimately, when the counter reaches the threshold value, we block the request. So here, the most important thing is a counter, because that is one of the highest level to track how many requests are submitted from the same IP address or from the same user, and how many should be allowed, how many should be rejected. So these all depends on this counter. So the counter need to perform in a well manner. So how do we store this counter? Where to place this counter? So that is something what I'm trying to illustrate here. So let's assume we are allowing 3 requests per minute for a particular user. So whenever a request comes in, what our rate limiter does basically is it will check first for the user ID. I'm just taking user ID as a unique key. So it first checks for the user ID which is present in the hash table or not. If it is not present, then it just inserts it. That means it's a new request which has come from this particular user. It inserts that and sets the counter to 1 and set a start time to the current time. That is what it does, and simply allows the request. Assume that it already has the user ID. It finds the user ID already existing. Then it tries to find a difference, between current time to start time. The start time is the time which is already registered in the hash table. It just takes the difference. If it is greater than or equal to 1 minute, if that is the case, then which means I still have a buffer under the 1 minute window. I'm there, and it sets the start time to the current time, updates, and count to 1 and allow the request. That is what it does. In case if the current time to start time difference is less than 1, and that means it is more than 1 minute, then and if the increment is already 3, we are allowing only 3 requests per minute. If it is greater than 3, sorry, if it is less than 3, it will allow the request. If it is greater than 3, it rejects the request. So the entire logic depends on this counter over here. So this is how I'm just trying to give you the flow. Okay, 1 second. So if you see, the request has come at 3 a.m. So we just inserted into the hash table. Ramesh is a user, count 1, start time. Now I got a request at 3 of 10 seconds. We just increase the count to 2, update the time. We just keep the start timestamp, and we just allow the request. Now, if you see of 3 of 1, which is after 1 minute, we just reset the count and update the start time. Just reset the start time also, because there's a change in the time block. So we say this is the start time now. And the count is reset to 1, and it's allow the request. Now let's say 3 of 1 at 20 seconds. We just increase the count. The start time remains the same in the same 1 minute window it is, and we still allow the request. And 3 of 1 45 a.m. 45 seconds. We have we see the count, it's still 2, so we allowed it. So we have count is 3, and now the start time remains the same. Let's say 3 of 1 at 50 a.m. Okay, we said only 3 requests are allowed. At 50 a.m., which is within the 1 minute window block, we see the count is already 3. Hence, we can't allow this request, and we just reject the request. Right? And let's say we get some other request at 3 of 2, which is after the next to 1 minute window. Then the counter will reset basically to 1, and the start time gets updated. So this is how the entire flow happens. This is a simple fixed window flow. We call this algorithm is basically called as a fixed window flow. We probably will not deep dive into this algo, but this is a basic algo which works in one of the algo which works in rate limiting approach. So here entire flow, what I'm trying to say is the counter is quite important. So where do we store this counter? I'm saying again, the counter is quite important for the entire logic. Where do we store? So we need to decide or think of a place where I can use time-based expiration techniques, and we have in-memory cache available. So basically, wherever these two I have, it's a better place to store the counters. And naturally, Redis is my best choice, because we have INCR command where the increment can be done automatically, just +1 without any much computation. The expire command, which I can use it to set the timeout for the counter. Counter automatically gets deleted, once the timeout expires. So these two are some other use cases where I feel Redis is the best choice to choose to store the counter. Now, as I told you, to implement this, the major algorithms we see is token bucket, leaky bucket, fixed window counter, sliding locks, and sliding window counter. In this, I'll take sliding window counter as an example, and I'll deep dive. Probably I'll also go through the sliding window algorithm, and then I'll take the sliding window counter algorithm to understand the difference, what is the impact, and then slowly we'll try to see the implementations. In this slide, let's understand about the rate limiting algorithms. As in the previous slide, we have seen there are four major algorithms that are used in the industry practically. Let me deep dive more into the sliding window algorithm, because from the questionnaire, since we want more on sliding window counter algorithm. So I'll start with sliding window and then go to sliding window counter algorithm. So this is one of the best image which I felt I can use it to explain the concept. Assume consider entries which have been coming in. Whenever we have a request coming in, we log those timestamps as an entry. So these are the all colored. If you see the red colored one, these are all the new entries which are coming. So here consider we have 5 requests per second as a rate limiting rule or policy defined. So whenever a new entry comes up, the timestamp gets logged in and the entry is registered. So this is how it happens. So consider a hash table where we store all these entries, and once we reach the threshold, which is 5 requests per second, the request which comes post that within the same time window, probably it gets rejected. So now post that 1 second, post that 1 second time, the window gets moved, slided towards the next. If you can see here, there's a sliding. That's why it's called as a sliding window model, where we'll have space to occupy one more request. So the next coming request will be occupied like this. As the time keeps on moving, the window, the window which has a capability to occupy our request will be sliding towards the new window box, and the request keeps on getting occupied. So here, if you see from one same request, if I get multiple requests, I have at 11 o'clock, I have one request. At 11:02, I have another request coming from the same IP. Every timestamp is getting registered here. So this, let's assume all these 4 are from the same client. Okay, we have all the 4 registered here, all the 4 logged in here. So like this, we store all these timestamp entries in the hash table. So now here, this is actually in overview of how a sliding window algorithm happens. Okay, now let's understand what is the problem with this implementation, where we get stuck up. So just to summarize, this is my time window. And these are the requests and these are the new requests. Within the time window, whatever request comes, it gets logged, the entry gets logged in, the timestamp gets logged as an entry. If it is the request is coming above the threshold, then they get rejected and the sliding window starts moving back. So this is the overview, right? Now with this, I'll go the major problem or the issue what we'll try to understand is, I will like to talk about the space complexity here. So here in the sliding window, which is not with a counter, there's no counter here, it's just a simple sliding window algorithm. The memory usage is high. We keep on storing all these entries, the timestamps of every request is being stored. So the memory usage is critically high. So let's understand, what is the size of memory it takes for 1 billion traffic. So at any time, if I want to monitor or track 1 billion users at any time, what is the total memory required? Let's try to understand. So if you are thinking the unique ID as user ID, assume that user ID takes 8 bytes of space. Each timestamp takes 4 bytes. And for a 500 requests per hour, I'm just considering it as a 500 requests per hour is my rule. So I'll be storing 500 entries in my hash table, right? So I have my hash table. So the overhead for the hash table would be probably 20 bytes. And the sorted set, which is a timing window, for that we have 20 bytes. So here the total memory would be the user ID, which is 8 bytes plus each timestamp which is getting stored. So this is calculated for the hash table, where 4 plus 20 into 500. The 500 is the total request which comes in a particular hour, plus 20 for the hash table overhead. So total it comes to be around 12 KB. And if you want to track 1 million users at any point of time, so you will be ending up totally 12 GB space. So this is how we analyze the space complexity. That means when the space complexity is huge, ultimately performance will become a problem. You'll end up need to read so many entries, and that becomes a huge issue in your implementation. So considering this, we'll move to the next algorithm with a sliding window algorithm using a counter. The same algorithm, the only difference is if I have a entry or if I have a request coming from the same client or a user ID,
Instead of adding a new entry, I'll use a counter. The counter gets upgraded. So here, in this example, if you see, just to make it clear, Christy is a user who has one, who hits at this particular timestamp. I just have a counter called one. And again, after 1 minute window, after that window, I have another request came in. So this is the new window. This is the old window timestamp. So we have count one. Under the same 1 minute, this is a O of 5, this is a 20. So 3 of 1 with 5 seconds, 3 of 1 at 20 seconds. So under the same 1 minute window, we have one more request came. So I've increased the counter to 2. Again, under the same 1 minute window, we have another request that becomes 3. Under the same 1 minute window, I got another request, but let's assume we have only 3 requests per minute, then we just reject this. We don't. Now we got 4 of 1, where I have another request came because the 1 minute window moved, so we can still accept that request. So this is how the counterpart works in the sliding window. So here the advantage is that we are not going to log every entry. If it is a similar request or request coming from the same client ID or user ID, we just increase the counter. That is the advantage, right? So now with this algorithm, let's recalculate the same space part which we discussed, the space complexity part. So consider the same user ID, which is 8 bytes, timestamp, which is required 4 bytes. We have another counter here, which is another 2 bytes extra. Let's consider. Now, same 500 requests per minute. To do that rate limiting, what is the size? And if you want to observe for 1 million users, what is the space ID? Let's see. So same 20 bytes for the hash table and 20 bytes for the sorted set. So total memory 8 plus 4 plus 2, 4 sorted set, 2 for the counter. 4 for the timestamp, 2 for the counter, and 20 for the sorted set into 60. See, even though I have 500 requests per minute in a particular hour, okay, in a particular hour, I can hardly have 60 hits because the counter keeps on counting. We have no new entry added. So it will be into 60 plus 20 as the hash table overhead, which is 1.6 GB, 1.6 GB. Now to track 1 million users, we have 1.6 GB. So if you see very clearly, there's almost 86% less memory utilization in the counter model. Whereas in the normal sliding window model, we have close to 112 GB space occupation. So as the space complexity comes into picture, it's always better we go with the sliding window with the counter model. Okay, that's how I want to give you the confirmation. So why we are approaching or moving towards sliding window with the counter model. Going to next, it's the same algorithm, in the local and in a distributed systems. I want to just compare, implementing on the local and for distribution. I'm going to a production level where I have multiple clusters. What should I consider? What problems I'll have, and how do I overtake? Before I start implementation, I want to this. So assume there's a user who sends multiple requests. Now these requests are queue via balances, load balances. And there's a rate limiter in the middle which checks, and then there's a DB at the back end which checks the counts. Now here, the problem which we face generally will be the inconsistency problem, which means like between when a request is when 2 requests are sent at the same time, the load balancer which is going from 2 separate balances, 2 separate rate limiters, they consider 2 are same. Assume there are 3 requests per minute is the rate policy for us. Now there are already 2 which is already consumed. Now we have only 1 left over. Now at the same time limit, when 2 requests are sent, the rate limiter, because in the database the count is still 2, considers both the requests as valid, and there is an inconsistency problem. We are allowing, we told the policy that it's only 3 requests per minute, but because of this distributed problem or inconsistency problem in the distributed systems, we allow both the requests. So this is a one unique problem, which we'll see in the distributed system. How do we tackle this problem? How do we say this? So there are 2 ways. One, but both the ways have pros and cons. So we have to end up taking something into consideration. So one is the sticky session. So if I have a request sent from a particular client via a load balancer, we'll ensure that always that particular user IDs or client IDs or IPs request goes to the same load balancer again and again. So that is how the sticky session concept is there. The problem with this we will be overloading the request from one particular user always through one load balancer through one instance. So this might overload, and it might sometimes kill that particular machine. So this is one kind of a fault tolerance design, but yet we need to see and understand how to take that next. And the next is when you're storing in the database, when the counter is getting stored in the database, we can use this Redis locking approach where when a request has come, via one rate limiter or via one load balancer, when I'm updating my counter, we lock it so that the other rate limiter, other services cannot update it. So this is how we can balance this inconsistency problem. But this will add another extra layer of latency, So this is a performance trade-off which we can think of. So we will see the best approaches how to use. Maybe using caching, we can still set up this locking approach in a better way. We will talk in the next slide on that. So this is how I want to deal with the inconsistency problem which we'll face in distributed system. Next, on the caching, as I told you, to solve the inconsistency problem, caching is best utilized. We have a important two-stage caching here. So, as I told you already before itself, counters are the one which gets stored in the cache layer, not on the database. Effectively, if you want to fetch and update and do the things, it's always better to store the counters in the cache layer. So we use the write back cache strategy, where the cache is first updated and then at a periodic intervals, we update the major storage, which can be a Mongo or whatever it is. So we can use this write back cache strategy over there. Okay, so that is one option which I want to say. So this way, what happens is your cache is getting first updated. Your lock issue, the latency problem with the lock will be resolved. That is one consideration. And also, whenever the timestamp has to be deleted, we can use the LRU, least recently used eviction policy, where if that particular entry is not being used, it's least used, then based on the TTL, we can evict it. So we can remove it from the entry. So this is also another advantage of using cache. So the problem which we have with distributed systems, the inconsistency problem, we have two solutions where one with the sticky sessions, other one is with the Redis lock. With the Redis lock, we see the latency, but to overcome that, we have this write back cache strategy where we can update it fastly and minimize that latency problem with the cache technology, right? Let's talk about the implementation part right now. So we'll see two important things under this implementation. One, the components under the APIs, what components are there, what is the purpose of each of the API or the microservice. And then we'll just go to the code level overview, probably a kind of a pseudocode, and explain you how it works. So first, I'll take you to the components. So these are the major components which will be a part of the rate limiting service, the entire workflow. So one is the rate limiting service, which is basically the decision maker. So I'm calling this as a decision engine. So a request which comes from ELB lands on this particular microservice first. This will be the central service, collaborates with all other services. This is the one where the entire computation takes place, the creation of hash tables, computing the timestamps, counter increment, all these logics, what we have discussed with respect to sliding window algorithm, that is written or drafted in this particular microservice, or so hence this is a core of this entire project. So the next is a rule service, basically to do all the CRUD operations on the rules, create, update, edit, delete. So whatever you want to do and store, primarily, as I told you, we store first in the cache and then we store in the DB. So we use this service to update and create new rules. I have a endpoint, I have a new endpoint. If I want to set some new rule, I use this rule service to do all the CRUD operations. The rules DB, as I told you, to store the rules. So we'll have primarily two. One is cache layer, which is Redis. The other one is a Mongo probably, which will, from cache, we have a job which runs in the background and sync these rules to the DB at the particular intervals of the time. And we also have a throttling service, background job, which keeps a sync, which is what I told you, which keeps in a sync to between these DBs. So that's how these components work with each other. So these are the major components in this project. These are the top level API design. I'm just moving on. So first one is the generate key. This method or the service basically is used to generate a key, unique key for every request. So if it is authenticated, then fine, we can use it as a user ID. But if it is not authenticated, so this method will generate one unique key for every request. Whenever a request comes from the same place or same IP, or we'll have the same key as our output. So first method is the key generation. Once the key is generated, this goes to the hello request function. The hello request function takes the key as an input and decides whether to allow this particular request or not. So that is how it takes. Now, to do this internally, what happens is allow request calls another service called get info for key, which will get the status of this key. The entire logic which we do, this method calls the status of the key. So under this function or service, we will have the timestamps, which will compute the current timestamp, and it will fetch the data from the Redis and see what is the previous timestamp for this particular key. So the logic works in the points which I mentioned. If the key is not present the first time it is coming, it just inserts into the hash table with a counter set to 1. And if there is already existing, if the key already exists, and then if assume the current timestamp, if it exists, there will be a timestamp. So what we'll do, we'll fetch the timestamp from the DB, take the current timestamp of the request, understand the difference. If it is within the 1 minute window and the counter is less than our config value, then we will allow this request. If we assume the counter value is more than the allowed value from the config, then we will just reject the request, and we'll wait till the window moves to the next 1 minute window. So this is how the entire flow works. These are the main key services we have in this app. So I'll probably walk through to one sample pseudocode kind of a stuff, which I'll share here, which is a collab interface. So I'm just most probably discussing here only on the decision engine. So allow request is my service which is being used here. This input is request key. So this returns either true or false based on the request. That is the output which is expected from this allow request API. And the request key can be a user ID or a unique key, which can be designed for the anonymous users. So for anonymous users, we can take the timestamp versus the IP. You can do a hashing of these things and get a unique key. Now, this is how the method calls. First, we'll have a config. So from the rule service, we update our default config, default rules for a particular endpoint, right? So we will fetch that and get what is the allowed number of requests for a particular endpoint and what is the window time. For 1 minute, for 5 minutes, for 1 hour, we have 500 requests allowed. So whatever is being configured. So we'll first get that particular from the configs, and then we will get the current time in the seconds from by using the time function. And then what we'll try to do is get the time difference. That's a start time we call. If it is within the 1 minute accepted window, we'll just check that using this method called get current window, where we pass the request key and the start time. So this window will return few things within the window. If the request is there within the window, within the threshold or not. If that is there, it will return saying, hey, it will have a value called number of requests, which is if it is greater than the capacity. We say it's only 500 requests allowed. And if suppose the request is some 501, which is greater, the window that request is greater, then we return false. If suppose it is less, then we call a function called register request, which actually updates the counter value, stores the value back to the hash table, and then returns a true value. So this is a simple pseudocode which works for this algorithm.